Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. I'm Hammadi Nait-Charif from Bournemouth University, UK, and my talk today will be about fall detection in supportive environment for elderly. As we live longer, and the number of elderly people increases in the society, there is a need to help those people live independently in their home environment. And the idea of this research is to extend the independent quality of life of people in their homes and subsequently reducing the healthcare cost. And if we use the technology for telehealthcare, where people are looked after in their homes, that's really something very, very important for both the healthcare and the people. And for today's presentation, I will be talking about tracking and recognition of activities and mainly detecting the unusual inactivity or falls. This is the setup we use. So it's a wide angle camera mounted to the ceiling. It looks down to the living room, which is one of the most used rooms in the house. So we have a sofa, we have a chair, we have a TV, coffee table. So the person would be moving around the house and he will be coming in and leaving the space. And we will be recording him for a long time, and we would recognize or learn the normal patterns. And from that, we would be able to detect the abnormal patterns and mainly falls. So to be able to do that, we used particle filters, and particle filters have become so popular in visual tracking that in particle filters, the probability distributions of where the person and the characteristic of the state of the person or the object being tracked are represented by probability distribution function. And this probability distribution function is represented by a set of samples. Each particle contains one set of values of the state variable. And to find an approximate solution using complexity, means the particle filters find an approximate solution using a complex model. It's an arbitrary probability distribution rather than using an exact solution using a simplified model. So it works like this. So we have probability distribution that we don't know. So it's not a known, it's not a defined function. So to be able to represent it, it's represented by a set of particles, and each particle is weighted, and you can see that the diameter of those particles is proportional to the weight. So then there is a sampling. So we sample from those, and you can see that those with high probability are sampled more than once. Then we add the prediction, or we predict where the person will be in the next frame. If we have a motion model, we use it. Otherwise, we use random walk as the example here. Once it's done, we would, the next frame, we will be looking into approximating or measuring the likelihood of those particles, as you can see here. So the well-known one is condensation, which was introduced by Blake and Israd. And the condensation, or the particle filter, as in its canonical or normal form, has a problem when the inter-frame motion is poorly modeled, and the case where the prior is not, and also the prior is not an optimal choice. It's not the optimal choice for importance function. So it does not take into consideration the recent observation. So always the recent observation that's coming from the frame at time t is taken into consideration for the finding the person in the frame t+1. And the representation of probability distribution functions by particles, to be able to represent it properly, does require a lot of samples. So we introduced something we called iterated likelihood weighting to deal with those problems with the condensation, and we divided the particles set into two sets. 50% of the particles are sampled from the posterior, exactly the same way as condensation, and the 50% of particles are used to increase the sampling in regions with high likelihood. And it does work like this. So on the left here you have the condensation, and on the right you have the iterated likelihood weighting. And you can see that after the first step, when we get to the when we apply the stochastic dynamics, we divide the particle set into two, the red ones, and we iterate those ones more than once on the actual frame. And you can see that the particles migrate towards the high probability where it's most likely to be to find the object. And you can see at the end here, if you see the particle filter or the condensation, there is only almost one particle on the left. There is only one particle representing the distribution, while actually if you look at the on the right with the iterated likelihood is used, you can see that we have the more particles where they are needed to be. So to apply that, we applied it to an application where we track the faces of people living or participating in a meeting. So we took the model or the model of the person. We looked at the head, so we used an ellipse around the head, and we weight it by looking into the gradient around the ellipse and the color histogram, the interior color histogram. And you can see here the example. I have this two, those are my son and my daughter. So if you move the ellipse from left to right, you can see that at the end of the when the ellipse is on the shelf, the gradient is high, but the color similarity is very low. And when you make the ellipse go to the left, the gradient is low and the color likelihood is low. And the same when you do you move the ellipse on vertical line. So when you look at the sides, if the ellipse is small, it still catches the right color histogram, but the gradient will be low. This is how you can see it here. So you can see the color, which is in black here. It's the way it's high even when the ellipse is very small, and the gradient is high when the ellipse is big. And the only way to combine them is to get the right weight is when you combine the color and the gradient, and you can see it there in red, where the highest value is obtained when the ellipse is just around the face of the boy. So we applied that to tracking people participating in a meeting. So you can see here that the first person is lost because he has moved so fast, and the same for the second one. So we lose the first one, then we lose the second, although we track the one in the middle now is actually the one on the left. So the yellow top is actually tracked as being the one with the black. So when the third person comes in, so he's well tracked, but the tracker, which was actually stuck on the poster, moves to that person. So this is what we get when we use condensation. But when we use iterated likelihood, you can see that here, even if that's actually condensation. So we'll move to next. So when we use the iterated likelihood, we can see that the person is properly tracked, that we don't lose him. The second one, we don't lose him either. And the third also, we don't lose him. So the iterated likelihood was able to track the person, the people all along. So for fairness, we ran the experiment 100 times for using condensation and 100 times using iterated likelihood. And you can see on the left here that the condensation lost track almost 50% of the times it loses the one or the other. It loses one and it loses the other. So it's quite bad in a way. And if you see on the right here where the iterated likelihood only 2 times it lost the person in yellow, and the person on with the black top was never lost. So it's quite a powerful scheme to track moving objects, especially when they can move suddenly in one way or the other. So to apply that to tracking the person in the house, so this is the way we went about it. We used background subtraction, and we used two ellipses, and we expect the small ellipse to be the foreground, and the ring around should be a background. This is how we want it to be. So the small ellipse, we want it all to be white to tell us this is the person, and the ring we want it to be black, means that's a background where the person is not. And yeah, this is how it works. So if you see here the two examples, you can see that although the person on the right has moved the chair, he was still being tracked properly. So once we have done that, we track the people for the person for a long time, so over something like, I think it's exactly 100 times, and we used Gaussian mixture to learn the inactivity zones. So this is what we wanted to do, is to learn from the extended observation, we wanted to learn the normal pattern of the person. We want to learn a context specific spatial model. So we want to know exactly where he sits, where he exits, or where he enters the room. So we used we clustered. The cluster should correspond to one with semantic spatial region, so it needs to be more meaningful. So we ended up with something like this. So we had the entrance to the hall, the entrance to the rear, or the exit to the rear. Then we have two places, two zones of inactivity where the person sits for longer period. It's one is in the chair and one is the sofa, one place in the sofa. And once we have done that, and what we used actually mixed Gaussian models, which are used for clustering. The Gaussian components correspond to inactivity and entry zones, and the entry zones are used to focus the tracker at the initialization. So now if I can go back here at the entrances, that's where we did a background subtraction, and we will be looking when there is no person in the room. So we will be expecting him to come from the entrance R or the entrance H, and that's where the background subtraction will be. So we took those trajectories, we segmented them, and we evaluated the performance by looking at how many atomic activities have been properly classified. And these are the results. I will show them here. So we had something like 270 atomic instructions. So you can see from the left here is you go from the rear to the hall straight away, or you go from rear to sofa, then rear again, and so on. So the inserted errors, so it means that things that were detected and they were not there, so it means they were inserted by our system, were 11. The ones that were substituted, means they changed, were only 1, and there was 2 which were deleted. So overall, the performance of the tracking and the classification was very, very good, and we were able to track the people and find their normal pattern. And when the unusual inactivity happens, then that's where we say that's fall. And this is the example. So the person is coming in, moves in. You can see the trajectory there is blue, which is just normal movement, the usual one. You get to purple. It turns purple when the person is inactive, where he is usually inactive. So it's a normal inactivity zone. Then he stays in for some time. Then he starts moving in again when the motion is still normal. then the trajectory is blue. But as he falls, the trajectory turns green. I don't know why we used green for that, but the person here is inactive in a place which is abnormal, and that's really unusual inactivity detected, and for us that corresponds to a fall. We applied that for other falls, you can see here, and we were able to detect all of them and find all the falls that happened in our database that we used. So just to summarize, that we were able to track the occupant and observe him for extended period, learn the unusual inactivity zones, where he sits, where he enters, and so on. And once that's done, it becomes easy to detect him when he's inactive in a place which is not usual, which is not normal. And that's what we did. So thank you very much for your attention. Hopefully I will be there, not just using the video. Hopefully I will be there presenting in the presentation and answering the questions. Thank you very much.